Welcome to my Handcrafted Transformers video series. I'm Dan Wilhelm. Together, we'll learn how Transformers work at a low level by building them from scratch ourselves. Each video will introduce new parts of the Transformer, and we'll handcraft the network weights instead of training them. We'll explain all the math and the coding along the way. And we'll solve real problems. In this video, we'll design a transformer that decides whether a sequence of numbers is positive, negative, or zero. We'll first design the transformer on paper, code it, then provide some exercises with solutions for your own practice. I'll also note the cumulative sum problem in this video was designed by Callum McDougall as a monthly challenge in interpreting pre-trained models, as part of his Arena Interpretability Bootcamp. So, if you'd like to see how a larger, trained transformer solves this problem too, I've linked to Callum's repo below. So, let's dive in. We'll walk through how the transformer will work with a simple example. So, starting off, we're going to start with a vector of tokens. And in our case, we're going to look and see whether the sum of those tokens is greater than 0, less than 0, or 0. So an example, and I'll call this in tokes, is going to be the numbers 0, 1, and -3. Now, what we're going to do is classify this as being positive, negative, or 0. And so if we sum these three numbers up, we get a negative number. And so we're hoping that the output of our model is going to be negative in this particular case. All right, now we'll take those in tokens, and the first step is the embedding step. So before we input these into the model, we have to convert these into vectors of numbers called embeddings. So you could imagine, for example, what if these tokens were words? Like, what if this was the cat is, right? If these were words, we can't just mathematically compute with words. So we have to convert each one of these tokens into a vector of numbers. And these are, again, called embeddings. So we'll do this in the next video. We'll actually work with words as our tokens, or letters at least. But in this video, we're going to just pretend that our tokens are numbers, and we'll just say they're from -5 to 5. And so I need to come up with a vector of numbers to represent these numbers. And so that should be pretty easy to do. And then it turns out this is going to be the input of our model, so I'll just call it x for simplicity. Well, we only have 3, so we'll do this. Now I'm going to encode 0 just using 0. And just for fun, we're going to have 2 channels in our model instead of just 1. Now, obviously, I could just encode this using a single channel because 0 is 0, but I'm actually going to use 2 just to demonstrate channels. And it'll actually come in handy later on. So that's the representation of 0. It's 0, 0. Now to represent 1, I'm going to write 1 in the first channel, and then the second channel will have a -1. So this is sort of channel 1 and channel 2. And then to represent -3, I'm going to encode that using the embedding -3, +3. Okay, so these are our embeddings. And this is going to be the input of my model. Remember, if these were, say, words instead of numbers, then I'd have to convert the words into vectors of numbers. But since they're already numbers, I might have it easy. Of course, it depends on the problem we're trying to solve what the best representation of these numbers will be. And then my first channel here is just going to be the number, and my second is going to be the negative. And this is completely arbitrary, and you can already tell this is redundant information. So I probably don't really need to have both channels, and we'll look at that later. Okay, so this is the input of our model, and I'm just going to call it x. For this video, I'm trying to make the terminology as simple as possible. So the next stage is we pass this into the attention block. And in a normal transformer, we would then pass the output of that into a multi-layer perceptron. Or you might hear it called a feed-forward layer. And then this represents one layer, and you can have multiple layers in your model. So the output of this would then just feed into the attention portion of the next layer. However, in this simple example, I want to make it as easy as possible. And so for this example, we're just going to use an attention block. In fact, we're just going to use a part of an attention block, as we'll see in a second. So we'll take the output of the attention, and I'll just call that Y, because that will pretty much be the output of almost the output of our model. Now, what does attention do, right? So in brief, basically, attention takes a weighted mean of our inputs, channel by channel. And I'll go through the math later in this video to show and prove that that's actually what it does. But for now, we're just going to pretend that it takes the mean of each channel. So what I would expect the output here to be is, in this particular case, I would expect, so for the first channel here, C1, the mean of this is 0 plus 1 plus -3. So this would be -2/3. And then for the second channel, you can see it's just the same numbers, basically. And so that would also be -2/3. All right, so this, we could say, is the weighted mean of X. In this case, the weights are all the same. Now, I am simplifying a number of things, because the attention block, technically, it takes the weighted mean, but it also does a linear transform of that. And again, later in this video, we'll walk through the exact details. But I'm trying to make this as simple as possible for now. Now, after the attention block, we're going to do an unembedding. So I have to take this vector here. So by the way, we call this the residual stream. And currently, the residual stream has the mean. Oh, and I messed up. The second one is actually positive, right? And it has negative of the mean. So we placed the mean and the negative mean on the residual stream. Now remember what we're trying to do, right? We're trying to compute whether the sum of a bunch of numbers is positive, negative, or 0. And what's the mean? Well, the mean is the sum of a bunch of numbers. It's just divided by the number of numbers. So if we look and see what the mean is, it looks something like this, right? So the mean is the sum of the numbers. Here, I'll put that in a box. So all I have to do now is I have to test this vector that I put on the residual stream, whether the mean is positive, negative, or 0. So we could possibly just look at this first number. But how are we going to do that? Well, the final step is the unembedding. And so to do that, I have to define unembeds. And so I'm just going to propose some. And generally what you want in your unembeds is you want to match the pattern. And I'll explain what that means in a bit. But for my unembeds, I'm going to just propose something like this. And this first row is going to refer to the positive class. The second row will refer to the negative class. And our final row will refer to the 0 class. And so what we'll end up doing is we'll multiply the output Y with these unembeds, which I'll call U for now. Now you can see kind of my strategy. Now I'm not doing any transforms here, any linear transforms. I'm keeping the unembedding space the same as the embedding space. And so you can sort of see what's going on, almost, with most of them, except for 0, which we'll talk about later. But with the positive class, you can see that, well, my first is positive. With the negative class, you can see that the first one is negative. And you can see it actually matches up with my Y, right? So my Y is -1, is negative something, positive something, and the negative class I'm saying is negative something, positive something. So you can see that they match up. So let's see what's going on here, right? When I do a matrix multiply. Okay, so I'm going to replace y with mine, negative 2/3, 2/3. And I just want to show you like what's going on here. So when I multiply these matrices, and this is y, I'm doing dot products. So when I only have one row in y, I'm doing the dot product of that with each row in u. And I should have transposed u, right? Or else this wouldn't have worked. So when I transpose u, I can do the dot product of each row in y with each row in u. And so let's see how this works. So I'm going to compute a score for each output class. Okay, so I'm going to, for the first one, for positive, it's 2/3 times 1 plus 2/3 times negative 1. And so what's the results? Well, that's negative 4/3. This is for the positive class. For negative, you can see that the signs line up. All right, so now I'm going to get a positive, negative 2/3 times negative 1 plus 2/3 times positive 1. So I get a positive 4/3 for the negative class. And then for my zero class, you can see that they're going to cancel out. Negative 2/3 times 1 plus 2/3 times positive 1. And so these cancel out to 0. So which of these three scores is the largest? Well, the negative class score is. And so that's our predicted class. And instead of scores, we normally call these logits. And we'll talk about why later. It's because we'll look at the exact reason why later, but they're called logits just because we plan on raising them, or we plan on exponentiating them. Because right now, these three logits are, some of are negative, some are positive, and it's hard to compare them. And so to compare them, we're going to exponentiate them. We'll see why later. And so what's actually going on here? Like, what's the intuition behind this? So let's look at that really briefly, right? So these are called the dot products. And let's see what's actually going on here, right? So if I take each one of these three rows and I plot it, here is the positive class, right? Because it's 1, negative 1. Then the negative class is a negative 1, 1. So it's the opposite vector. And then the zero class is 1, 1. So I can draw it like this. And so what's going on is with my final output is negative 2/3, 2/3. And so if I draw that here, it's approximately, did I get that wrong? Oh yeah, negative 2/3 is down here. 2/3 is right here. And so it's right here. And so here is my y. And you can see that the vector of my y lines up with the negative class vector, right? There's a 0-degree angle between them. And because there's a 0-degree angle between them, we classify it as negative. Pretty cool, right? And that is the intuition behind how the dot products work. Because if we take a dot product, like if we do y dot ui, let's say, well, this is equal to the magnitude of y times the magnitude of ui cosine the angle between them. And so if it turns out if you normalize u and y and make them unit vectors, then they're equal to the cosine of the angle between them. But of course, here in LLMs, they're not exactly the angle because we don't normalize them. So their scores, their logits, are slightly dependent on the magnitude as well. So it's not the exact angle, but it can also be based on the magnitude. So that's the intuition behind why these work. Now, I skipped over a few things. In an actual LLM, and what we're going to demonstrate today, our y is not just two numbers. What actually happens is in the attention block, we're going to make predictions for every subset of tokens. And by that, I don't mean every subset, but I mean we're going to make a prediction after the first, after the first 2, and then after the first 3. So instead of just predicting negative for this, we're going to pretend that we start with only 0. And so our output is going to be for 0, 0. And then we're going to pretend we have 0, 1. The output for that is positive. And then we'll pretend we have all 3. And so the output for that is negative. And so what an LLM actually returns is it returns a predicted label for an increasing subset of the tokens. So, when you use ChatGPT, for example, you only see one final prediction. But actually, it makes a prediction for for the next word, for every word in the input sequence. Kind of crazy, right? So next, let's take a look at what y will be, okay? So before, it was just one vector, but in actuality, it's going to be many vectors. Okay, and I'll put it by the side so that we can see that. So our output y is now we're going to have one output per subset. Okay, so our first one is just the first. So the mean of 0, 0 is 0, 0. Then the second is going to be the first 2. So the mean of that is going to be 1/2, negative 1/2. And then for all 3 of them, as we just saw, it's negative 2/3, 2/3. So this we'll call it the cumulative mean. This will be the actual output of y. And then when we pass that down here, we're going to make 3 predictions. So because now y is 3 outputs, we'll take each row and we'll calculate the 3 logits for that row. So here we're hoping that 0 will have the highest logit. Here we're hoping that positive will have the highest logit, and here we're hoping that negative will have the highest logit. And you can confirm that yourself if you'd like. And so we'll end up with 3 different predictions, 1 per token, because we have 3 input tokens. It sounds complicated, but we're going to walk through this in code right now. So first, let's just go from the top to the bottom. We'll specify our in tokens, and we'll just use the example that I made. One thing to know, if you're going to use NumPy, you should use NumPy. So instead of using a Python list here, let's convert it to an ND array, n-dimensional array. And then, of course, it's always good to look at what you just did so that you can verify it. Okay, so we need to have a bunch of embeddings, right? And for our embeddings, we're going to store a number, and it's negative. For each number in a range, okay, so we said at the beginning of the video that we're going to accept from -5 to 5. And so we have to come up with an embedding for each one of those. So we'll call a variable max value to be 5. So this will go from -5 up to +5. Remember, these ranges, they're exclusive on the upper end. Okay, so I have to go to +1 to capture up to 5. So our max value we'll set to 5, and this will allow -5, -4, -3, -2, -1, 0, and then 1, 2, 3, 4, 5. So this is 11 tokens in total. All right, so let's look at our embeds here. Looks pretty nice, right? So by the way, when you look at this, this is a matrix, right? And we have 11 rows corresponding to our 11 tokens. And then we have 2 channels is what we call these, channel 1, channel 2. So I'm going to make another variable here called k. I'm calling it k because I need a really short variable name. I can't call it num tokens because I use k a lot, as we'll see. So this is, instead of 5, we have 2 channels. So 2 channels. Okay, so if I were to represent this, and I'm going to remind you continually what the dimensions of our matrices are, because when we do matrix multiplication, you always have to verify the dimensions. All right, so here we have the number of the number of, this will be our vocabulary size, so I'll call it n vocab. So we have 11 tokens total, so the vocab size is 11. And then each one has 2 channels. So it looks like that. Okay, so that looks good. Now I have to just look up these 3 tokens. And it's not as simple as it looks, although it's pretty simple. If I just type in tokes, I don't get the right ones. So only integer scalar arrays. So you see what's going on here. I have a -3, and I can't just look up -3, right? And so when I look at my embeds, if I want index 0, that would give me -5. I don't want -5. I want the 0 embed. So what I'll have to do is I have to add 5 to each one of these, right? Because the number 0, the token 0, is stored at index 5. And if I want -3, I'm going to go to index 2. So that's -3 plus 5. So when I look things up, I'm going to have to look up intokes plus the max value. Uh-oh, only integer scalar arrays can be converted. Now, if you get this, it seems, you see, I forgot to convert my embeds to an ND array. And now it works as expected. All right, so I've got a 0, 1, and -3, and that corresponds to my 3 input tokens. What's the size of this, right? Well, the size of this is n tokens by 2 channels each. So I have n tokens rows because I have 3 input tokens, and then I've got 2 channels along. I'm just going to leave in, by the way, when I make mistakes, because I know a lot of you following along probably also will run into some errors, and so hopefully that'll help. Hopefully that'll help you debug some. All right, so I called this x up here. X is sort of the input to our model. This is the beginning of our residual stream. Our residual stream is going to enter the attention block now. So we're going to have to code that up next. I'm going to leave x sitting here so that we can see it. All right, so now let's code up attention. Now, this is really interesting. So for attention, we're going to have to take the mean of the inputs. And, you'll have to believe me right now that taking the mean is something we can do. And I'm going to walk through the math after we do the practical example, after we code this up. Because I know for many of you, the coding is more interesting. For some of you, the math is more interesting. But I'll show that this ends up being exactly what we code up here is exactly what the attention block does. All right, so now let's take the x. Now, one thing I could do is I could just take the mean. Now, when I say mean, I have to be very careful about how I do it, because there are many different ways we could take the mean. If I just take mean of x, I wonder what that will return, right? Well, it returns 0 because it basically flattens the array and takes the mean of them all. And you can see that these all sum to 0. So the mean of all of them is 0. And that's not what we want. We want to take the per channel mean. So I want to take the mean across the rows. Okay, in future videos, we're sometimes going to have 5-dimensional matrices. And so it's important to be able to work with axes very fluently. Okay, so I want to go and take the mean across the rows. And when I say across, I mean that we're basically going to collapse that axis. And so we'll be left only with the 2 dimensions of the columns, as you can see right here. And that's exactly what we got for the final one, -2/3, 2/3, in our computed example. Now, just if you have a 2-dimensional matrix, you can remember when you think about a matrix, you usually go rows, then columns. And so axis 0 is the rows, axis 1 is the columns. Now, this isn't entirely what we were hoping to do, though. We were hoping actually to get the cumulative mean for each increasing subset of the tokens. So this did work for the final one, -2/3, 2/3, but I want it to work for every cumulative one. So let's see how we might do that. It turns out NumPy is our friend. So let me just print this so that we have it. There's this function called cumulative sum. And if I run the cumulative sum, you know what? I should probably also print the in tokens just so that we have it. And I'm just going to specify what these things are. This is the final mean, right? All right. So we have this cumulative sum, and what that does, if I just run it without an axis, it flattens the array, right? So the first cumulative sum is 0, 0 plus 0 is 0, 0 plus 0 plus 1 is 1, and it goes so on. Now this is 0 again, now this is -3, and then this is 0. This is not what we want, right? Because I want to take the cumulative sum, but I want to go, again, row by row by row. So I'm going to have to specify an axis along the rows, because I want to collapse the rows. Okay, so now you can sort of see what's going on, I hope. The sum of only the first row is 0, 0. The sum of the first two is 1, -1, right? Because 0 plus 1 and 0 plus -1. And then the sum of all three is -2, 2, if I go up and down the columns. Okay, but this isn't the mean. So to commute the mean, I'm going to have to divide by how many elements, right? So if I just have the first token, I just have 1. If I have both of the first two, I have 2, and then I have 3. So all I'm really doing here is I'm looking at, I'm computing a range, just like I did a range up here, right? And we're going to start at 1, and then we'll go up to the number of tokens, and that's just the length of intokes. Now, remember, in the final one, I have 3 tokens, and the upper bound of this range is exclusive, so I'm going to have to add 1 again. Now, it doesn't quite work, and you're going to run into this problem quite often. The problem is that if you look at the cumulative sum, we have a 2-dimensional array, and when I do this division, I want to do the division on something that is columnar, right? I want to divide the first row by 1 and the second by 2 and the third by 3. But the problem is this is assumed to be a row vector instead. So I'm just going to have to reshape this so that it goes up and down instead. And maybe it's best if we just take a quick look at this A range, right? So you can see it sort of looks like a row vector. It's just really one-dimensional. But I want to reshape it so that it's a column vector. Okay, so we'll have 3 rows and 1 column. So you can see now it's a column. You can see now it'll line up with the cumulative sum, and we can do the division. And now you can see it's exactly over here what we predicted, right? So the first column by itself has a sum of 0. The second has a sum of 0.5, and the third -2/3. And by the way, remember, this is 2 channels that are always the opposite. The first channel is the mean so this is the mean of only the first tokens embedding. The second one is the mean of the first 2 tokens embeddings. And the third is the mean of all 3, right? So it's important to sort of understand that. I'm going to call this the weighted sum, the weighted mean, by the way. It's important to understand that, but to know where that's coming from. I know it's a little bit complicated. So now I've got this weighted mean, and we're just going to pretend right now that that's y. So I'm just going to set y equal to the weighted mean. We'll do a little bit more with it later when we walk through the math of attention. All right, so now if I look at y, we've got this exactly like up here. And so now I just need the unembeddings. All right, so let me print y so we have it. So now I just need these unembeddings. Let's define them. And I'm just going to convert this into an array so we don't forget. The first is 1, -1. The second is -1, 1. The third is 1, 1. And again, you can see these line up with everything but 0. And so we'll have to come back to 0. 1, -1 lines up with this one. -1, 1 lines up with this one. And these are our 3 classes. So our first class is the positive. This will line up with negative. This will line up with 0, we hope. Okay, so now let's just do this matrix multiply, right? So first off, what are the dimensions of each of these, right? So for y, we've got n tokens, comma k. For these, we have the number of classes, comma k. So you can see these will line up if I take the transpose of this. Okay, so I'm going to do y at unembeds, but I can't just naively do it like I tried to do before, or else I'll get an error. And that's because when I try to do this matrix multiply, you can see that the inner dimensions do not match. And so I'm going to have to transpose this. If I transpose it, now the inner dimensions match. And remember, when we do this transpose, here I'll write it as it should be. When I do this transpose here, what we're actually doing is we're taking each row of y and we're taking the dot product of that with each row of the unembeds. So we'll have to do a dot t. Now, is that what we got over here? In fact, it is. For the final row, I only computed those. So we got -4/3 for the positive class. We got +4/3 for the negative class. And we got a 0 logit for the final class. And so now we have to take, so these are our logits. And so now we just have to find which one of these numbers is largest. Okay, so to do that, and these will be our predicted classes. All right, so for our predicted classes, we're going to use argmax. What argmax does is it returns the index of the largest number. And so for this one, the largest number is the first, so index 0. For this one, the largest number is index 1. And for the first one, they're all the same. And because they're all the same, the way argmax is designed is it'll just take the first. So we'll have to fix 0 later. So the other thing to note is argmax, again, it requires an access because I want to return 3 different argmaxes. So note here, I'm going to go across the columns instead of across the rows. Okay, so I'm going to set axis equal to 1. All right, because I want to, for each one of these 3 tokens, I want to find the class that is largest across the columns. I want to collapse the columns down. So when I look at the Y predictions, here I'm predicting the positive class, and the negative class. Is that what we looked at? Well, yeah, 0, positive, negative. So this is positive and this is negative, and we have to fix 0. Okay, now it would be easier to understand this if maybe we let's just have a mapping. Let's map these indexes to classes, right? So 0, just so we keep it in mind, is the positive class. 1 is the negative class, and 2 is the 0 class. So what I'm going to do down here is let's just make a little list comprehension. So for class in ypreds, we'll just output classes class. And these are our predictions. All right, and this is our y right here. Pretty nice, right? Okay, now for 0, we're going to have to dive into the attention block, and we'll have to understand what math we have available to us to try to make the 0 class actually work. But you can see right now that as it stands, it's actually not possible to detect 0. Because when we want to detect 0, y is 0, 0. And so 0, 0 times anything is going to be 0, and 0 will never be the largest logit, unfortunately, given how we've defined positive and negative. So there's no way right now to detect 0. So we're going to have to invent a way. And let me, just for, here I'll make a new cell. Let's just move all of this stuff into one cell, just so that we can look at the entire model like all at once. I should probably make this, well, I'll just leave it as it is, because this is a constant, right? Let's move this up so that we can see, we don't need the final mean. Here, let's print our logits, I think. That would be nice. So basically, I'm just moving this up so that we have the unembeds I should put up here. You can see I'm kind of being inconsistent with my constants, I guess. But and then you can see each step very easily, I hope. So this is attention. This is our so you can see we have 3 sections, right? So we have the embeddings. So this is like section number 1. And then we have our Right here, we have our attention block. And then finally, we have the unembedding. Okay. So far, so good, I think. You know, it looks like a little bit of code here. Just for consistency, we'll do that. And it all fits on one screen. And this is actually what an attention block can do. So we've created our first simple model. Our zero class doesn't work yet, but we'll make it work once we understand what's available to us mathematically. All right, so the next step is we have to understand some of the math behind the attention block, because we have to know that this actually is what we were hoping to do. Okay, so let's dive in and take a closer look at the attention block. So with attention, I'm just going to throw the formula at you here so that you can clearly see it. So with attention, we're creating this y, and we're going to take our input, and remember we called the input x. So the way I'm showing you right now, this is sort of the classical way of describing the output of attention. So first, we have a few linear transforms. So we'll take the input x and we'll transform it using a value linear transform like this. So these are called values. This is the value projection. And just so, again, so you know the dimensions, this is k by k, right? K is the number of channels. And then for BV, these are called biases. And this is just a 1 by k. So there's one bias per channel. And this is called a linear projection. So after we transform the inputs, typically this is described as we then multiply by the weights. Okay, so these are our attention weights. Now, most people describe attention as computing the weights. So in our case today, we're just going to assume that these weights are already computed and that all the weights are the same, 1 over n. But attention has the ability to make different weights, right? Think about this. So here is a weighted mean. We might do something like that for our weighted mean, I equal 1 to n. So what we can do is if we have some words like the cat is nice as our tokens, what we can do is we can put different weights on each token. And remember, each of these tokens is a vector of numbers, right? So maybe this is 0, 0.3, 1.7, and so on, right? For the. So each one of these is a vector of numbers. And so when I put a different weight on these, maybe I could make this 0.2, maybe I could put a lot of attention on cat, and then nothing on is, and maybe just a little bit on nice, right? So these are going to be our weights. So the idea is that these attention weights allow us to place attention on each of the tokens. Now, one thing to note, this token, when I'm saying tokens, I mean the residual stream, the input to the attention block. They're only directly associated with tokens in the very first layer. But after the first layer, they could be like scratch work, or they could be, the input to the attention block could be a complex transform of the input tokens, right? But that's the whole point of attention. It puts different weights on different tokens when it calculates the mean. And in a few videos, we're going to walk through exactly how it does that. But because this part by itself is a little tricky, I don't want to introduce too much complexity right away. Okay, so we first transform the inputs, then we weight those transforms. Now, if you'll notice in the code, I actually weighted the inputs directly. And so I'm going to prove to you that that's actually identical. But after we do this, after we weight them, we then subject it to another linear transform. And this is the output projection. And it's also k by k. So let's do a little bit of matrix math. Okay, we're going to use some identities here. And I'm going to prove to you that what we did is identical to this. It's going to be crazy. Okay, so first off, Let me see if I can scroll down a little bit. First off, what we'll do is we'll just use the distributive property, because when you do matrix multiplication, you're allowed to distribute. And so it's going to look like this. I'll first just distribute with W, right? So it looks like that. And then I can distribute with O. Well, before we do that, maybe we might want to use associativity. Okay, so just as a reminder, with associativity, you can change the order of the parentheses. And it just so happens that associativity holds with matrix multiplication. The thing that doesn't hold always with matrix multiplication is commutativity, right? So if you have AB, it doesn't necessarily equal BA. Okay, so that doesn't hold, commutativity doesn't necessarily hold with matrix multiplication. But let's use it here, right? So you can see I've got BC and I've got A. So let's actually swap these. And then I'll also do the distributivity with O. Okay, so we've got WX, V, right? And then I'm doing the distributive, WBV, O plus B. So far, so good, right? By the way, you can already see that I've changed it. Well, I've used identities to prove that you can just take the weights directly on the inputs, right here. I'm just taking the weights directly on the inputs. Pretty crazy, right? All right, now let's get rid of some of these extra parens. I'm going to use associativity again on this first one. And this time it's a little harder to see, I think. Let me see. Yeah, so this will be A. This will be B. Okay, so I'm going to use this one. And I'm just going to rearrange this slightly. Now I'm doing this because I can now treat VO as a single matrix, right? So it's a K by K times a K by K, which is a K by K. So this whole VO thing is just a K by K matrix. And now for the tricky part. Now you might be saying, well, this still isn't exactly what you told. So you can sort of see the outline here. If VO is the identity matrix, then I've just got this as a weighted mean, which is exactly what I showed you. But you could say, well, I've got all this other stuff, and that's dependent on the weights. So what's amazing is that this quantity here, the weights times the value biases, that's actually just equal to the value biases. I can get rid of the weights entirely. By the way, what I'm showing you here is a technique you can use on any LLM that follows this math, which is most. It allows us to look at it in a new way. And it allows us to get basically make the value biases 0. And we're going to end up simplifying this quite a bit. So let's take a look at this final part here, this WBV. So we looked at W before, not really, but it's the weights, but we have weights for every single one of the subsets of tokens. So our weight matrix ends up being the number of tokens by the number of tokens. And each one of these sums to 1. We haven't looked at the reason why, but these are basically like probabilities. It's because we take the softmax of each row, which we haven't looked at yet. But because we take the softmax of each row, it ends up that they sum up to 1. And so then, we're doing a matrix multiply here by BV. So we have BV1 all the way up to BVK, because we have K of these. There's 1 per channel. Now, when we do this matrix multiply, these don't exactly match up, right? But we're going to apply these biases. These are constants. And so when we do this matrix multiply in NumPy, we're going to actually broadcast it up. So we're going to end up with this being n tokes rows. And we'll just copy these vectors upward, these constants. So you can probably see where this is going, maybe. Okay, so now we have this matrix times this one. And we're just, so after we have these weights here, this is just, we're taking each row and we're taking the dot product of each row with each column. And you might be able to see where this is going. Let's work it out. Let's try this first one, right? So the dot product of this first one is going to be B V1, so it'll be the first one of here, we'll just call that W1, plus W2 BV2, B1 again, plus W n tokes times BV1 again. And we can factor out the BV1, and we get W1 plus W2 plus Wn, and we set up here that all of those are equal to 1. So this is equal to just BV1. So it turns out this matrix multiply is just equal to BV. Crazy, right? Because we made each row of the weights sum to 1. And so up here, this actually just simplifies to B plus, I know it's crazy, but this just simplifies. And this is just plus BVO plus BO. And we no longer have a dependence on the weight. This sum here is just a constant. And so, because that sum is just a constant, think about this, right? So now we can just say, let's make this B prime V equal to 0, and we'll make BO prime B equal to this quantity here. And we can rewrite this as WX VO plus BO prime. And that's the output of attention. This is Y. Pretty crazy, right? So this is actually a transform. This is called folding, and you can do it with any LLM that follows this math, which is most of them. We're folding the value biases into the output biases, and it all works. And so you can see probably how this corresponds to our code. Let me show you the code again. Okay, so we have our WX, which is the weighted mean. Let's just make it line up more perfectly, right? So let's make our VO. Our VO matrix in this case is a K by K matrix, right? So this is a K by K. And so we'll just use the identity. And then we'll do a matrix multiply of the weighted mean at VO. And this should give us the exact same result. And then we have these biases. And the biases are 1 by K. So I can just do something like that, and we get the same result. Okay, so now this lines up exactly with what the math of attention says it should. And we folded the values and proved that there's this effective output bias. And we can define what that is. Right now, just 0, 0. So now we have two additional things that we can play around with. We have the VO matrix, and we have these biases. Well, remember how I set the 0 vector to be 1, 1? Well, what if I set this to be along the 1, 1 direction? So that when it's 0, we're going to be facing this upper right direction. Okay, so let's try it. So if I put a 0.01 and a 0.01 here as my bias, when this first part is 0, then I'm going to be pointing in the upper right. And when I'm pointing in the upper right, down here with the unembeds, we're going to compare it to a vector that's pointing to the upper right. And so we'll get a match. Let's see, I'm going to run this one more time. There we go. As our 3 predicted classes, exactly as they should be, right? Because the first token is 0, and so the sum of 0 is 0. I think I'm printing logits, but I put Y there. So here are the actual logits, right? So you can see now that I have this bias, I'm adding it to everything. And so what's going to happen now is this will be a constant 0.02 because the first two will cancel each other out. As far as, when I multiply each of them by 1, one of them's negative, one of them's positive, so that'll cancel out, except for the 0.01s. And so 1 times 0.01 is 0.01, plus 1 times 0.01 is 0.01. So I get 0.02 as a constant for the 0 logit. And so when it's actually 0, the first two logits will be 0, and this one will be slightly larger, and it'll be the winner. Let's try some more. Like here, I have my in tokens. Let's modify this, right? Like what if I make another 0 at the end? If I do a -2, well, I don't think I did that right. I should make this +2. And so we end up with 0 again. You can see the first two logits are 0 for positive and negative class because they cancel each other out when I multiply them with a 1, 1. And then all that's left is this bias here, 0.01, 0.01, which results in 0.02 for the 0 class logit. Pretty cool, right? So now we've written something that should work with a lot of things, right? So let's try -4 here. So you can just put in as many numbers as you want, and you can even put in just one. There's a positive and there's a negative. There's a bunch of numbers, and all of the math just works out. And we proved here that it's actually equivalent to what the attention block actually does. Now, one final step that might be useful that you see these things do is it doesn't just predict the most likely class, but it gives you probabilities. In this particular case, I think that probabilities won't really help us because we know our model works perfectly. So why bother predicting what the probability will be, right? Well, I think this is actually a good place to look at the probabilities because it shows that probabilities aren't necessarily what you think they are. So the way that I think of the probabilities are they're just scaled logits. They're just scaled output from the model. They're not really probabilities. Like if one is 80% and one is 20%, that doesn't mean it's like 4 times more likely, right? It just means that it's a scaled output of the model, which I think is important to keep in mind when you assess these probabilities. It's also very easy to change the probability distribution, as we'll see. So let me just walk you through how we compute probabilities. So we use what's called the softmax. And so naively, let's just look at probabilities in general. Like, let's say I have a coin in my hand and I'm flipping the coin. So the probability of heads is going to be the number of times I flip heads, let's say 48, divided by the number of trials, right? And so the probability of tails, then, I'd have to have 52 out of 100 trials, and this gives me some probabilities, right? And so naively, if we were to implement this, I would just do, so I have my logits, right? And I want the probability of each class. So what I could do is I could just, take, so for example, for this 0 one, I could just take the total sum here, which is 0.02, and I could take each one of these and just divide by the total sum. And then I would get a 0 probability, and then for the final one, I would get 100%, because it's the only one with any value. Let's try it, right? So for the logits here, I'm going to do the sum, the total sum, but I have to do it across, right? So our axis is going to be 1. Okay, so all of our total sums are the same, of course, because the first two classes are opposite. The first two logits are opposites. Well, they're approximately. No, they're exactly opposites. Yep. So now I'm going to have to take each one of the individual and divide by this. But you may have noticed, this isn't going to line up. Okay, so I'm going to get an error. So we're going to have to do the same strategy. I'm going to reshape this so that it's a column vector instead. Okay, so just naively, this is how you would maybe try to predict the probabilities, right? But the problem is that it worked for the 0 class one because all of them were non-negative numbers. But for the others, we had negative numbers. And you can see over here, when we look at the probability of heads and tails, this only works if all the numbers are positive. So we need a different way of doing this. And the easiest way of solving this problem is let's just map all the negatives to positives. And you might think, well, there's an easy way to do that. Maybe I could just add the minimum. And you could, but the minimum is really hard to work with. Like if I try to take the derivative, what is the derivative of the minimum number, right? So there's a much easier way to do it. It's just let's apply a function that transforms negative values to positives. And the easiest way to do that is the exponential function. We can just raise them all. We can do e to the number, and then that will make it a positive number. So let's try it. We'll do the exponentiated logits. And then we'll just do exponentiated logits, just like that. And so then down here, instead of logits, I'll use the exponentiated logits. And you can see it mostly works, right? So here, let's print the in tokens just so that we can see. So the first one is 0, and you can see, it has a slightly larger probability, but not really. Then for the second one, the sum is 1, so that should be positive. Sure, that works. Then the next one should be negative. That one's the highest probability. And then we're 0 again, so technically it's a higher probability. And then we're back to negative. And so we can see that negative has the highest probability. And of course, the larger our number in that direction, the larger the probability will be. So this kind of works. Now so a few questions, right? Well, let me just write for you what this looks like, right? This is called the softmax, and it requires a vector of numbers, and it requires some index. So we're going to take e to the x sub I, and then we'll divide it by the sum of all the others. So j equal 1 to k. So it looks like that. A few questions, right? Why are we using e? Why not use something convenient like 2, right? Well, e, it turns out the derivative of e to the x is e to the x, so it makes it really easy to take the derivative of. And for training purposes, that's important. Another thing is, when we do this, can we make the probabilities larger? And we can look around and try to do that. Like, what if we scale the logits? Like, what if I multiply them by 10? Wow. Well, that certainly made a lot of difference, right? So when we multiply them by 10, it sort of just slammed our most likely classes for the positive and negatives. And we still have a little bit of trouble here on the zeros, though. Now, why did that happen? And this is one thing you should keep in mind when you're using the softmax. When you're using the softmax, if you have a small difference, it'll make it a huge difference. All right, like think about this. Like I'm going to instead of e, I'm going to just approximate that with 2. But like if I have 2 to the 10 versus 2 to the 11, well, this is 1024 versus 2048, right? So this difference was originally a 1, but now the difference is 1024, right? So it magnifies differences. And that is the key to understanding how these just exploded and suddenly they're 1. And just by controlling this multiplicative factor, I can like vastly change what the probabilities look like. What if I divide by 10? Well, now they're much more equal to each other. And this is one reason why you don't really want to trust them as probabilities in LLMs, because they're so easy to change this. It's so easy to change this distribution. Sure, the order is still going to be the same, but the probabilities, you can make them vastly different just by changing this factor. So keep that in mind. Another problem with softmax is numerical instability. So what happens if I multiply this by a large number? Well, I get overflows. Other than overflows, though, I also have problems that are a little bit hidden. If I raise something or if I do e to the power of something, then I get a large number. But the problem is the way we store those numbers using floating point, it results in lower precision. So when I'm around 0 in floating point, I have very, very fine precision. But with floating point numbers, the way they're stored in computers, with large numbers, I jump much farther distances as I increment my number. So it turns out if you use really large or really small numbers and store them in floating point, you're losing precision. So there are definitely a few disadvantages to using softmax like this. Okay, so I'm going to take this. Let's not multiply it by a huge number. I'm going to take this and just add it to our final implementation. And this gives us the probabilities of our final classes. And, you don't have to calculate the probabilities, by the way. You can just use the logits if you're trying to only predict what the most likely class is. Because, when you do e to the something, when you exponentiate something, it's still in the same order as it was before. It's monotonic. Okay. Whew. So just as a review, we take the embeddings, then we pass it through the attention block, which is just, a little linear transform here. Then we do the unembedding. We calculate how similar it is to each one of the unembedding vectors by basically calculating sort of the angle between them. And then we find the probabilities and the final predicted classes by using the softmax. And this is the softmax. Okay, I have a few challenges because you shouldn't just watch a video. Hopefully you're coding along as well. So here are a few challenges for you, and you can pause the video and try these yourself. And these, I think, are fairly straightforward based on what we talked about. So the first challenge I have is, let's take a look at these probabilities. So up here, what I was doing was I was multiplying the logits just directly, but you're not allowed to do that, right? You have to follow the model, right? So I can't just, after the fact, multiply them by 10. So can you make the probabilities close to 1, but inside the model? And you have 3 opportunities for doing this, right? You could do it in the embeddings, you could do it in the attention block using that formula, or you could do it in the unembeddings. The second is, now that we have the probabilities close to 1, because we know that we're perfect, would it be possible to minimize the model? Because so far, remember up here, we're using 2 channels initially. It would be nice, because this just has redundant information. It would be nice if we could just use 1 channel. So can you make the embeddings a single channel? Now you can still use 2 channels later. In fact, you should probably think about whether 2 channels are required at the end. But can you just reduce the embeddings to a single channel? And then third, let's do a theory one. Can you prove that adding a constant to each channel results in the same softmax probability, we'll say. So here are your 3 challenges. If you want to try them, which I suggest, pause the video now. Okay, so let's walk through these just to make sure you understand the model. I'm just going to copy our code here. This is a lot of code, so you probably are going to want to refactor it into some functions and such. In fact, I'm going to take our constants and put them in a separate block. And I'll put the in tokens at the very top. Yeah, a lot of people ask, hey, how can I make a library? Well, what ends up happening is you have so much code, you want to refactor it and put it into functions. I'm not writing functions right now, and I should be. But I want it all to be on the screen so that you can very easily read it and very easily tweak things. So we're leaving it as is for now. Okay, the first challenge is, can we make the probabilities close to 1? And, we mentioned we have lots of opportunities to do this. So all we have to do is we want the final logits to be like multiplied by 10, right? Let's just use a simple example like that. So all I have to do is anywhere along this, I can just multiply the thing by 10, right? So for example, if I want all the numbers to be multiplied by 10, I could just make the embeds times 10. And you can see here, well, now the probabilities are really close to 1, right? Instead of multiplying those by 10, I could multiply the VO matrix by 10. I get the same result. Or I could multiply my unembeds by 10. So I put them up here. You can see I get pretty much the same result. But interestingly, you can see that it worked a little bit better on the 0 class, right? It's because the first 2 cancel out. And so, this is multiplying my 0.01s by 10 now instead of 0.01. And the other 2 cancel out. So this is still better. It would be nice if I could push these 0 classes a little higher. I have 2 ways I can do that, right? I could modify it here in the unembeds, or I could just make these a little higher. But you have to be careful when you modify these because these are added to everything. So if I make these too high, it'll change all of my probabilities, right? Now these are so high that I've pushed my vector so that it's always toward the upper right a bit, right? It's always closest to 0. So you still want this to be kind of low, but maybe we can make I don't know, I didn't do the math, but there we go. That's pretty good. Right, so now it's 0.05. Now, ideally you do all the math and you make sure that this is still always going to work. But you can see by making this a little larger, I've now biased it a little bit more toward the 0 class in general. And because my unembeds are so high now, this pushes the rest toward the probability 1, and this is exactly what I expect from a perfect model, right? Okay, so that does a pretty good job, I think. So we'll check that one off the list. Can we make the embeddings a single channel? And yeah, that's a good idea because these embeddings currently are just redundant. They're the same thing twice. So if I remove one, then the problem is when I run this, I'm going to get these matrix multiplies aren't going to work, right? Because if you think about this, the weighted mean is ntox comma 1, but my VO matrix is a 2, 2 matrix. Okay, and you can see the inners 1 and 2 don't match up. So I'm going to have to modify VO. So for my VO, I'm going to want this to be 1, but I still want to output the negative, so I'll output -1, right? So I want my VO matrix here to be 1, 2, so that the ones match up. And then in the end, you can see from the outer ones, I end up with an ntox, 2. So I end up with 2 channels per token. And this -1 ensures that the second is the negative mean. So now if I run this, it still works exactly the same way. But we've optimized, right? We've made the initial channels only 1 channel each. So that requires less memory, fewer computations, etc. But I should note, this is not how you normally make a transformer. Normally, the residual stream is the same size throughout the entire transformer. Something else that I just want to point out, because I think it's important. I like these exercises because we get to play around with some of these parts of the whole, right? Something I want to point out is a lot of times in a larger network, we transform the space. Okay, so a lot of times we start in the embedding space and we transform it through attention to another space. And I just want to show a simple example of how you can do that. Because you may have noticed, like, the way that I've set it up, our embedding space and our unembedding space are exactly the same. Like 1, -1 is in the direction of positive for both. But what I can do here, I can make a simple example where I rotate the space. Like, what if I do that? What if the negative mean is in the first channel and the positive mean is in the second? So I'm basically flipping this. I can also flip what the 0 class is too. Like I could add negatives, right? We'll just see what happens here. Okay, so now I've changed from the embedding space and I've transformed it into another space. And let's just draw what that space looks like. I could just leave these, I think. Okay, so now instead of positive, this one's negative, and instead of negative, this one's positive. And my 0 is now in this direction. So I'm going to have to modify my so if I just try this, you can see now we're getting it wrong. I should probably print out my intox here. But the first one should be 0, but it's classified as positive. The second one should be positive, but it's classified as negative. This one should be negative, but it's classified as positive. So I'm going to have to go up here and change my unembeds to another space. Right? So now if we look at my diagram, positive is -1, 1. Negative is 1, -1. And 0 is now -1, -1. So you can see how our attention block can transform the space. And this is what frequently happens in real transformers. Okay, so here are our in tokens. Let me get rid of these logits because I think they're a little annoying, and I'll print the intox. Okay, so our predicted classes are now, the first one is 0. The sum of the first 2 is positive. The sum of the first 3 is negative. Sum of the first 4 is 0 now. And you can see they're again correctly classified. So by doing all of this, I transformed my space from the embedding space to the unembedding space. Pretty neat, right? Okay, and then for the final challenge, and we're going to use this identity later. So for the final, we just have to prove that adding a constant will not change the softmax. So let's do that really fast. Okay, so let's say I add a constant. So what that'll do is to each x sub I, I'm going to add a c. Okay, so e to the xi plus c. And then remember, it's the same constant for every value in each row. So now this is xj plus c. Well, what's that equal to? Well, if my power is the addition of two things, I can turn that into two multiplications. And so now when I do the division, I do the same thing. For some reason I'm thinking x. Okay, so now I can, because all of them are multiplied by the same constant, I can pull that constant out in front like that. And because e to the something is always positive, I can cancel. And so this is our original softmax. End proof. So we just proved that if we add a constant to each value in a row, then that's identical to the original softmax. This is an important identity to know because, for example, it tells us that we can mean center something before it goes into the softmax and we'll get the same output. And by mean centering it, you can actually make it easier to interpret because then it'll have a mean of 0. It's also important for some things we'll prove in 2 videos when we look at the first part of attention. How does it compute the weights? So we'll use this identity to simplify a lot of the math. But I think that's it for now. In the next video, stick around and we're going to use this same architecture and we'll show how you can use it to compute things about natural language distributions of words and letters. So stick around for the next video, and if you enjoyed it, please like and subscribe. See you next time.